So we'll do chapter 24 today, hopefully chapter 25 on Thursday, which means homework. I'll try to let this homework be due this week, and chapter 25's will be next Friday. I have it due on Friday right now, that's good enough. All right, so electromagnetic waves, otherwise known by physicists as light. In the previous chapters, we've been dealing with some equations that together comprise a group of equations that we call Maxwell's equations, named for this guy, James Clerk Maxwell. And the reason they're called his equations is because he was able to solve these. These equations all have the same variables in them. They don't really show them here. I'll show them to you because they're not going to try to solve them in this class or anything. In a senior level electricity and magnetism course, you'll actually solve them the way that Maxwell solved them. But let's take a look at these equations. They are let's see, there's a better...
There's a website, Maxwell Dax Equations.
Oh, I know there is. I know it. I'm going to look at this one here. So this gives us two different versions of the equations right here. This is called the differential form of the equations, which is probably a little beyond most of us in this class. However, this one is maybe a little bit more understandable. This symbol you may be familiar with if you've taken a calculus course or something like pre-calculus. This is the integral symbol, and what it means, all the integral symbol really means is that you're going to add up all the different things beyond this symbol. So in this case, we're taking an electric field times an area. This dA is a little piece of area. So you take all the electric field that's going through all the areas in the region, and that has to equal the charge that's enclosed by that area divided by epsilon naught. And this is the equation that we used to calculate the electric field. This is essentially Coulomb's equation, where you use the charge to calculate the electric field or the electric force. And it's called in this form, it's called Gauss's equation, and this is what's responsible for calculating the electric field. This one here is a similar equation, and it's often called Gauss's equation for magnetism. But in this one, when we have electric field times along a length, we get a change in magnetic field through an area. So that's kind of like calculating the magnetic field through a coil. You might think of it as that. That's right. Yeah. So and it also tells us something about the magnetic field near a wire, right? So this one here is actually what we consider kind of like the Lorentz law, the Lorentz equation. It's let's see. Yeah. No, sorry, this one is not Gauss's law for magnetism. This one's Gauss's law for magnetism. This one is the Lorentz equation. And there's another name for it. It's also called, trying to remember, it's not Ampere's law, it's, can't remember all the time. But anyway, this one is Gauss's law for magnetism, where you have this, you take this, add up all the magnetic fields going in and out of an area, and they end up equaling zero. That's essentially the law that tells you that all magnetic fields always loop around and reconnect to themselves. And then this one here is Ampere's law, where you have a current that flows, and it creates two things. You get a changing magnetic field, which is this one, and you get a changing electric field, which is this one. So a current creates a magnetic field, but it also creates a changing electric field. And so that's Ampere's law. And if you look at all these, each one of these has the same variables in it. You have electric field in these three. In these two, you have magnetic field. Actually, in these three, you have magnetic field, right? In some of them, you have current. You have current in this one. And you have current, actually, technically, this is current over here. So you have a lot of things that are kind of cross-pollinating in these equations. And it turns out that you do have enough equations to get a solution to this system of equations. And when you do solve it, you get a solution that looks kind of interesting. So the solution that you get looks like this, or this, either way. In fact, any one of these is a solution. But these solutions, they may look kind of crazy and funky, but what you get is you get something changing in time on one side and something changing in space on the other. And when you have something that changes in time and space, we call that a wave. And there is let's see if we can find a nice algebraic version of this. Probably not. Instead of a calculus version. They don't really show it. But we're going to see it here in just a minute in our book. So that's fine. But what you get is you get a wave. So Maxwell, he solved these four equations that were all about electricity and magnetism, and he got a wave that was kind of surprising. He didn't expect to get an equation that would show that when you mix electricity and magnetism, you get a wave. But it actually all made sense in the end when he looked at one particular part of the equation, because there's one particular part in that equation that tells you the speed of the wave that you're interested in. Let me actually open this up really quick again, because I'll show you which part of the equation that is. So when you're looking at this solution here, the one part of the, let's see, they don't really show it explicitly here. Right here. This, well, that's not even it either. Oh, that other equation was Faraday's law, that I couldn't remember the name of. Faraday's law and Ampere's law. And then when you solve it, you get an equation that looks like right here. If this is your wave equation, this thing that's in front of this time-changing thing, the thing that's in front of this is usually the speed of the wave. It's usually 1 over the speed of the wave squared, actually. But whenever you have a wave equation, you have something changing in space equals something changing in time. There's usually a constant that's in front of one of these two things that's related to the speed. And that constant just happened to be these two constants that we've dealt with before, the permeability of free space and the permittivity of free space, mu and epsilon naught, which are things that we've dealt with before. But when you take this 1 over the square root of those, which would be the speed of the wave, that's when he found this really interesting kind of strange thing. And that really interesting kind of strange thing is that speed was actually the speed of light that had been measured by many, many scientists. And so what he discovered is that these two constants, remember these two constants we've dealt with, mu naught and epsilon naught. Mu naught we dealt with magnetism, epsilon naught we dealt with electricity. Those two things, you multiply them together, take the square root, take 1 over them, and it's equal to the speed of light. And that's what Maxwell discovered. So he said maybe light is actually a wave of mixed electricity and magnetism. And through some different experiments, they were able to determine that that is true. They already knew that light was a wave by this time. They just didn't know what kind of wave it was necessarily. They knew that light was a wave because Thomas Young had actually done some experiments to show that light was a wave, which we'll learn we'll see in some later chapters here. So they knew that light was a wave, they just didn't know what kind of wave. And so now they knew, and they were able to do some experiments and learn some more about it. And they know that light is a wave with this speed, 1 over square root of mu naught epsilon naught. If you solve that, you get 3.0, you actually get 2.99 times 10 to the 8 meters per second. And the physicist Heinrich Hertz, whose the frequency is named for, the unit of frequency, he was able to demonstrate that you can create light using an electromagnetic circuit. So this electromagnetic circuit is a resistor, an inductor, and a capacitor, which we just dealt with, right? This circuit builds up a resonance, and then he put a transformer in there. On the other side of the transformer, he put in essentially an antenna. And this antenna had a little spark gap in it. It created some electromagnetic radiation. It created some light, radio waves, that would transmit through the air to another antenna, where it would induce some sparks in a spark gap here, and you could actually tune your receiver here to resonate with that incoming wavelength. So he was able to demonstrate that this light wave is created by electricity and magnetism. So how do we produce these things? It's really quite simple when we start to think about it from what we know. But the people who are trying to figure this out, this was not trivial, because this was the first time it was being done. But the idea here, the very simplest way that you can think of it, is that you have an alternating current source that cranks charges up and down a rod, which we call an antenna. So at one point in time, it's pushing the electrons to one side of the rod, which means the other side of the rod has lots of bare protons. And then at some other time, it's pushing the electrons the other way, and the positive charges on the other end are bare of electrons. And it's just doing this back and forth and back and forth. But as it does this, this creates an electric field that's pointing one way towards the positive charges, and then the other way towards the negative charge. It goes from the positive towards the negative, right? So at this point in time, the electric field is going from positive towards negative, and then later on it's going from positive towards negative, so it's now going down. And in between, it has varying magnitudes of electric field that are changing up and down and up and down. It varies up and down, up and down. But what did we learn when you have a changing electric field because of a current that's flowing? You also have a magnetic field, and that magnetic field, according to the right-hand rule, is pointing 90 degrees to the electric field change, right? So if your electric field is going up and down, then your magnetic field is actually going in and out of the page, right? Because of this right-hand rule thing with the current going up or down, you have an electric field or a magnetic field induced 90 degrees to it all the time. So when you put them together, this is kind of what it looks like. You have an electric field going up and down, which is the blue, and a magnetic field is coming out of the page and then going into the page and then coming out of the page and going into the page at the same time. And that is what a light wave is. The problem with this little picture here is that it's certainly not to scale. And each axis has a different scale. One axis is in volts per meter, which is the units for electric field, right? And the other one is in ampere, meter, something, whatever magnetic field is measured in, which is Tesla, right? So you have volts per meter for the electric field up and down, and you have Tesla on the other axis. So they're completely different axes. But the other problem is that the ratio in the magnitude between these two sides is actually like the speed of light kind of size. So the electric field is millions times bigger in its units than the magnetic field. And the magnetic field for light is generally quite small. Very, very small, very difficult to detect. So when we're trying to detect light, we usually try to detect the electric field. It's much, much stronger. So if you take the electric field magnitude divided by the magnetic field magnitude, you will get the speed of light. That is the ratio. So right here, we actually use this little equation, this little ratio thing, to calculate the magnetic field. If we know the strength of the electric field, which is the easy thing to calculate. So in this case, if it's 1,000 volts per meter in the electric field, what is the magnitude of the magnetic field? You rearrange that equation so that magnetic field equals electric field divided by C, and you get magnetic field is equal to 1,000 divided by 3 times 10 to the 8, so it's 3.33 times 10 to the minus 6. A microtesla, right? Microtesla, even for a magnetic field, that's kind of small, right?
So what's a small c?
Small c is the speed of light. 3 times 10 to the 8, or 2.99 times 10 to the 8 meters per second. So that is the ratio between the electric field strength and the magnetic field strength in an electromagnetic wave. It is equal to the speed of the wave, the speed of light. So the electromagnetic spectrum is truly infinite. But the only part that we really think about as light, in the normal world, is this little tiny sliver of it where our eyes can actually detect the light. So we've got red on the far left end of this little sliver and violet on the far right of this little sliver, and outside of that, we've got this huge spectrum, all these different frequencies that our eyes cannot detect, that are the same thing as this little sliver that our eyes can detect. This is the same kind of waves. They're just either lower frequency or higher frequency, which means longer wavelength and shorter wavelength. If you go to the left here, you're going longer and longer wavelengths. So the wavelengths are up here actually. Your wavelengths are, for the visible light, you're in the hundreds of nanometers. On the red end of the spectrum, you're at about 900, 800 nanometers. On the violet end of the spectrum, you're down to about 400 nanometers. So we can only detect with our eyeballs about a 400 to 500 nanometer range of this stuff. But if you go much longer if you go longer than nanometers and you get up into the micrometers, microns, a millionth of a meter, you're into the infrared region and into the microwave region even. The microwave region takes you into the millimeters and centimeter range as well. So microwaves are used, of course, we usually think of them as microwave ovens, but microwaves are also used for communication quite a bit. Most of your handheld radios, all your cell phones, Wi-Fi, those things are all in this range, this microwave range. And then you have TV and FM radio, which are right up along this meter range. So they're both into the meters, a few meters long in wavelength range, and they're also into a range of frequencies that we're kind of used to dealing with, which is the megahertz and the kilohertz frequency range. So let's see. So FM radio is into the hundreds of megahertz, and AM radio is down into the hundreds of kilohertz or thousands of kilohertz, which is also the megahertz range. And the number on your radio station is actually the frequency. So 97.4, for example, is 97.4 megahertz. So it's almost 100 megahertz. So it's right into this range here. And TV is also in those, but they don't name the TV stations after the frequencies. AM, so if you're at 1040 AM, that's 1040 kilohertz, which is 1 megahertz. So it's down here into the 1 megahertz and 1000 kilohertz range, AM radio.
The hertz is the...
Hertz is the frequency.
Yeah, but that's also the standard unit of measurement.
It's a standard unit of frequency measure. It's
So
cycles.
megahertz or micro
That's right.
You gotta change it, or
That's correct. So it's cycles per second, or it's waves per second. How many waves go by in a second? So as we're going up and down into this range, our frequency is going down, but our wavelength is getting longer. So our wavelength's getting bigger, our frequency is getting smaller. Till we get out here into you can get radio waves, really, really, really long radio waves that have very, very low frequencies. You know, these are the frequency ranges that you use to send things to submarines. Very, very long frequencies that can be actually that can actually go through water, for example, because it takes a longer wave to travel through water. As you go above our visible spectrum here, you're increasing in frequency, and the frequencies up here aren't really given names because the frequencies that we see at are at like 10 to the 14, 10 to the 15 hertz. We don't really have a name for those, but we do, but we don't use them. They're just really big frequencies with just huge numbers, so we use the wavelength, which is 420 nanometers, 500 nanometers, 600 nanometers. You know, that's just easier to use. But you get much shorter wavelength than 400 nanometers. We can't see it anymore, and we get into the ultraviolet, we get into the X-rays. These light rays are so short that they can actually travel between the atoms of things like metals and things, and skin and bone. So X-rays are just short, and that's really why they can travel through things. It also has a little bit to do with their frequency and their energy, but well, not a little bit, a lot to do with that. But the length of the wave plays a role in that. And then if you get really short and you start getting into the 10th of a nanometer down to the 1 nanometer and smaller, you're getting into gamma rays. Gamma rays are so short in wavelength they can pretty much go through anything, and they have a huge amount of energy as well. The higher you go in the frequency, the bigger you go in energy. The shorter you go in wavelength, the higher you are in frequency, the bigger you are in energy. So that was actually determined, well, it was discovered actually just in the past century. That was discovered in the 20th century, that this frequency relationship with energy is so prevalent. At first they thought it was amplitude. The brightness of the light was what made your energy which made your energy bigger. And it's true that the brightness of light does increase the energy a little bit, but they discovered that the frequency of the energy is much more important. And you can think of the waves of water in this way. You have waves of water that have amplitude, and that can bring in a lot of energy, but also the number of waves that hit per second can bring energy, right? So if you have one big wave, that brings a lot of energy, but if you have a whole bunch of little waves that come really, really quickly, that can actually bring more energy.
But it takes more energy to make the wave move up and down?
Particularly with light, the frequency, bringing that wave more often, increases the energy because what's a good way to think of this? It allows more of that energy to act on the material that it's hitting or whatever it's encountering. Instead of just one big wave with one amplitude, with a big amplitude of bright light, you can have a lot of light hitting, in a short amount of time with the high frequency.
It takes more energy for each displacement.
You can think of it that way. It's the things that I'm giving you are just analogies, because when we really start dealing with how light interacts with matter, we have to stop thinking of analogies eventually. And that's going to come fairly soon here. Because light is so small and it interacts with atoms on such a one-on-one basis, and we can't see atoms. We can't see how that works. We just have to go off the available evidence. So we're going to try to limit the analogies from here on out. That's just kind of to give you an idea of what's coming.
So we're guessing.
Yeah. It's not that we're guessing. No, we have evidence. We have information. But the problem with science today, in general, the problem with science in general for all time, not just today, is that we always have assumed that we understand certain things about science because we understand certain things about the world around us. So we look at a monkey and we say a monkey has fur, and then we assume And we know that the monkey has fur to keep it warm, or whatever the monkey has fur for. And then we assume that because an insect has little things that look like fur, that the insect has those to keep it warm. What's that? Well, it may or may not be true, but we assume that in science. Those are the kinds of assumptions we've made in science. Now, with a bug, we can actually look at the bug and observe it and start to figure out that maybe that fur is not there for its warmth. And we can make these visual observations. We can cut it open, we can watch it do things. With atoms, we assume that atoms and light behave in certain ways because we see light behave with a mirror. We see light reflect off of a mirror, or refract through a lens, or bounce off of an object and show its color. But we can't look at an atom to confirm that that assumption would be correct. And it turns out that our assumptions were driving us crazy with the things that we were actually observing in the science, the evidence that we were actually getting. So the evidence that we were getting and our assumptions were constantly clashing with each other. And so scientists who are studying light in atoms and light in matter had to completely divorce themselves from their assumptions and had to create a new kind of science. And this has affected all kinds of science. Because once scientists started to figure out that their assumptions were screwing up their science, they started looking at all science and figuring out that it was not just screwing up physics, but it was screwing up everything. We had made all kinds of assumptions that were not correct, and we've just kind of been living on those assumptions for hundreds of years. And this is the big thing that Einstein and other scientists of the 20th century gave to science. They gave them this idea that maybe their assumptions were wrong, and we need to observe, we need to redo all of science. And so the 20th century was huge in that way. A lot of assumptions were thrown out the window and reevaluated so that we could understand why things happen from the evidence and not from our assumptions, not from our tacit assumptions. Something that had not really been done very well before. Okay, so different kinds of, we've got the different kinds of electromagnetic frequencies and wavelengths here. Here are some rules that have come from observation, come from the evidence. High frequency electromagnetic waves are more energetic, and they're able to penetrate things more than low frequency waves. Okay, so your high frequency waves have a tendency to be able to go through objects better. High frequency electromagnetic waves can carry more information per time than lower frequency waves. So if you're trying to carry a lot of information, you need higher frequency. The shorter the wavelength, probing a material, the smaller the detail it will resolve. So in other words, if you're trying to make an image of a material, it's better to use shorter wavelengths to make that image. So blue light makes a better image than red light. Green light makes a better image than red light. And this is, we can actually observe this with our eyes. If we filled this room with nothing but red light, I should get some red lights in here. Your visual acuity would go down dramatically. Have you ever been in a room with a lot of red light in it? I'm assuming you have since you've been in the military. Your visual acuity goes down. You can't resolve things as sharply. But if you're in a room full of green or yellow light, you can really, yellow light is obvious. That's the light we live in. We live in yellow light. Right? That's the light from the sun. The light from most of our lights is slightly yellow. That light is a higher frequency, shorter wavelength, and we can really see sharpness of objects.
Yeah, but isn't there some animals that see better in red light?
No. There are some animals that can detect red light better so that they can see better at night, for example, when there is more of the red light than there is the yellow light. So they can see better than we can at night, but it doesn't mean that they can resolve images better or see more detail at night, because you just can't. Animals that can see better at night, quote unquote, can just see more objects. They can see more objects with I guess the way to say it is that the contrast between the background and the object is bigger than it is for us. but still they would still have the same fuzziness of perception. They're not going to see any more detail than us, because that's a physical thing, not a physiological thing. So the answer is not necessarily. But they're used to that. So, they can still do things like hunt at night because they can see the objects contrasted better. You don't really need to see detail to hunt unless you're hunting something very small. In the case of, for example, bats hunting something very small, they're not using their eyeballs. They're using a different type of detection to do that. So, okay, so transmission, reflection, absorption. Objects all matter when it encounters electromagnetic radiation, does these three things to it. The electromagnetic radiation might transmit through it. It might reflect off of it. It might be absorbed by it. It might do 2 of these things, 3 of these things. Usually there's a mixture of all 3. Transmission is to go through, reflection is to bounce off, and absorption is to literally be absorbed by the material. One thing that they don't say here is emission, because when a material absorbs something, usually there's some kind of emission, re-emission. So it absorbs one electromagnetic wave and then it emits another one. So that also can happen. So an interesting thing that you may have observed in your car is when you're traveling under transmission lines, you may notice that your AM radio station might go a little wonky. You ever had that happen to you? No? Do you listen to AM radio very much?
No.
Not many people do anymore. But I like to listen to AM radio. I listen to sports a lot on AM radio, and I like to listen to talk radio quite a bit. And AM radio stations, AM stands for amplitude modulation. That means that the signal, the voice signal or the sound signal, is created by changing the amplitude of the AM frequency. So the amplitude gets bigger and smaller and bigger and smaller, and that change is related to the voice coming over, or the sound coming over the radio station. Well, when you're near a transmission lines travel along at kind of similar frequencies to AM radio stations, and they have a huge amplitude of voltage traveling past. And so that huge amplitude of voltage, because the voltage is at hundreds of thousands of volts, at the kind of similar frequency, creates an electromagnetic wave coming out from those wires. And that electromagnetic wave interferes with your AM radio station and causes static. It doesn't affect FM radio. FM stands for frequency modulation. And in FM radio, what they do is they have a frequency, they have a carrier frequency that is carrying the sound. And then they have side bands on the frequency, 2 little frequencies that are a little bit higher and a little bit lower than the carrier frequency. And those frequencies on either side of the main frequency are vibrating back and forth in frequency. So the frequency is changing a little bit on those side bands. And that vibration of those sideband frequencies give you left channel and right channel for stereo sound. And one of them both of them are carrying the actual sound that's being carried by the radio. So those frequencies correspond to the audio frequencies that are carried. So when you go under these big high power transmission lines, that amplitude change in those transmission lines not an issue, because it's not changing frequency in the transmission lines like the frequency in the FM radio, but also it's not about the same frequency as FM radio. FM radio is a much higher frequency than AM radio. It's about 100 to 1,000 times more. So they're not in the same kind of band. Here you have this extremely low frequency wave that can travel very long distances and be picked up by these very low frequency waves can be picked up by fiber optic. And so what you do is you trail a fiber optic that's super long behind a submarine that's underwater, and that fiber optic floats to the top and just floats along the top of the water. But in order for it to pick, in order for this thing to pick it up, that very, very low frequency, this thing has to be super long. That's like hundreds of meters long sometimes. And
Isn't that really how cells communicate? They don't drag it.
yep, that is how they communicate. That's the ELF and that's the ELF communications that they use. So when they're underwater, this is the only way they can communicate with anything above the water. And the reason that they use this is because you can send the signal out from wherever. You can send it out from the United States, and it has to be sent from a big antenna because it's a really long wave. So it can't just be sent from a satellite, because satellites don't have big enough antennas. They're too small. So it has to be sent from something with a big antenna. And usually that means from a ground-based station that has antennas, hundreds. And because it's from a ground-based station and our submarines are all over the world, you have to send this long frequency so it will travel that far, because long frequencies travel further. But because it's such a long frequency, or such a long wavelength, it's carrying very little information. Remember, higher frequencies carry more information. This is a long wavelength, so it's a low frequency. So it carries very little information. It might carry 1 letter per minute or something like that. Well, maybe not that bad. Maybe 1 word per minute. So it could take a half an hour for a very short message to get through the ELF system. It takes so long for these messages to get through. But you know, they're submarines. They got time. They're sitting around there at the bottom of the ocean, not making any noise. You know, for them, a really fast attack. The fast attack boats in the U.S. Navy, they might take an entire day to attack another submarine. That's a fast attack. You know, they take all this time, and when they do attack it, they attack it from like 5 miles away. They launch a torpedo that's in quiet mode, and it just kind of tracks into this submarine that's 5 miles away, and then when it's in its last 1,000 meters or something, it ramps up to high speed and does active pinging so that they actually can hear it. But then by then it's too late to try to run from it. So submarining is a slow business. So this long wavelength thing is no big deal to them. So anyway. What's that?
So it'd be fun to go on submarine for a couple months.
Yeah,
It's
it
not
sounds.
fun to be on a submarine for a week.
Well, the first week is okay because that first week they have fresh food. After that, it probably really sucks. I've heard that when you go out on a submarine, for the first few weeks, every space on the submarine is filled with fresh fruits and vegetables, fresh meat. Every little space they can find, they stuff it full of fresh food so they can have fresh food as long as possible. Because for those last 2 months, it's just eating just the food that can be refrigerated, the food that lasts that long. You know, you get no more fresh fruits and vegetables. It's all canned, and it's terrible after that. They spend like thousands of dollars for their first few weeks of food, and then after that, they're just like, oh, this is terrible. Anyway. And the best captains are the ones who buy the best food for their crew. Okay, so anyway, here they show us this idea of the amplitude modulated. So this is what a wave looks like for AM radio, where the frequency stays the same, but the amplitude changes. So this outside black wave is actually the sound wave that's carried by AM radio. But with FM radio, and this is a bad representation of it, but this would show, this is just what they call the sideband. The sideband would look like this, and the audio signal, when it's put on top of it, changes that sideband frequency so that it gets longer and shorter in wavelength, or gets lower and higher in frequency. So that's what they look like. And the calculation of this is just like the calculation of waves in the last chapter. Wavelength is equal to speed over frequency. But with electromagnetic waves, the speed is always the speed of light, c. It's always 2.99 times 10 to the 8 meters per second. With water waves, it wasn't that. You know, with other waves, the speed would change. But the speed of light in a vacuum or in air is pretty much 3 times 10 to the 8, and that's it. It does change when it goes into materials, but we'll not talk about that or deal with that until later. So you can calculate the speed of something that has, you know, a 1530 kilohertz AM radio station. That's 1530 times 10 to the 3 cycles per second, or hertz, and you take your 3 times 10 to the 8 and divide by your frequency, and you get the wavelength. 196 meters for the wavelength of an AM radio station. For FM radio, quite a bit shorter, 2.85 meters, right? For a cell phone, 0.158 meters, 15 centimeters, right? And this is actually the reason that some people are concerned about their phone being a problem with their brain. Because 15 centimeters is about the width of your head. And so if you have that phone up next to your head, and that wavelength gets inside of your head and starts bouncing around inside of your head, they're worried that it will build up and build up. You have all kinds of electromagnetic radiation building up inside of your head, which is, a slight possibility, I suppose. Except that you'd have to have like a metal box around your head, because metal is the thing that makes microwaves bounce around. It's the thing that makes pretty much all electromagnetic radiation bounce around. And so if you've looked at your microwave before, your microwave oven, there's a microwave oven right here. This glass door is not just glass. What's on the inside of the glass? It's a metal mesh. You can see it on this side. There's a metal mesh in it. And there's metal on all sides on the inside. And that's what allows the microwave to bounce around on the inside of that box. Not only that, but the inside of that box is specifically designed to be a specific size in every dimension, a specific length in every dimension, so that the microwaves that this microwave creates fit exactly inside that box so that they will constructively interfere. Remember constructive interference? So that when it bounces back, it builds up on itself. And that's exactly how microwaves work. You have this particular wave that just happens to resonate with water. It just happens to make water bounce up and down or vibrate back and forth. But the waves in the box are matched up perfectly so that they build up on each other. They build up on each other exactly so that inside the microwave, those waves get huge and that water really vibrates and the oil in the food really vibrates. Oil and water vibrate at very similar frequencies so that you get your food heating up, right? So why would you have a rotating table inside there?
So it heats up all the way up.
Well, yeah, because you're going to get peaks of hot, and you're going to get places where it's not peaked, right? So if you just heat your food in there, you're going to get food that's got hot spots every however long that wave is, right? Or half that wave. You're going to get the hot spots in your food. But if you rotate it and your food is slightly off center from there, which it always is because you can never put it exactly in the right center. So you put your food in there and it's slightly off center, it's going to shift those peaks around a little bit and allow a little more, a more even heating of your food.
So if you put the set in exact center, you have the rings in the box?
Yeah, if you put it in the exact center, you'd have rings in your food, which would be kind of fun. And you can actually use this. The reason I bought these microwaves is you can actually use these microwaves to measure the speed of light, because you can measure the wavelength of the light in there. And if you look on the back of the microwave, it tells you the frequency of it. And if you have the wavelength and the frequency according to this equation right here, you can calculate the speed of light. Wavelength times frequency is the speed of light. And you can we'll do that in this class. We'll fill up a plate full of chocolate. We'll take the turntable out, fill up a plate full of chocolate bars and put it in there, and we'll microwave it and we'll take it out and we'll see the little dimples from where the waves were. We'll measure the distance between, that's your wavelength. We'll calculate the speed of light.
And then we'll eat the chocolate.
And then you'll eat the chocolate. What kind of chocolate should we get?
Dark chocolate.
Ghirardelli, the good stuff. I usually, with my physical science class when we do that lab, I usually just get the like Hershey's or whatever. But maybe for this one we'll get the good stuff.
You got more importance than that.
That's right. All right. Anyway, so and it's kind of funny because the frequency that microwaves work at was discovered by a guy with a chocolate bar. Have you heard this story before? So there's this engineer. He's working on the Cobra Dane radar array in Alaska. So the Cobra Dane radar array is the biggest, was the biggest radar array in the world. I don't know if it still is. But it's this huge radar array up in Alaska meant for spying on Russia. So this is what it looks like. This thing is humongous, right? But it's this huge array, and this guy was climbing up inside this and on top of it, and they've got this big scaffolding next to it for doing all this work on it. And he was working on it one day, and it was freezing cold, and he had a chocolate bar in his back pocket for a snack. And when he got down, it was melted. And he's like, it's like 100 degrees below zero out here. This chocolate bar was nowhere near my body. It was on an outside pocket. He's like, how did this thing melt? And as he thought about it, he thought, well, maybe it was the radar array. And so he went and looked at the frequency that the radar array was operating at that time. And he started experimenting with it, and he discovered that that frequency actually resonates with water and oil in foods. And he invented the very first microwave oven that way. He was able to build an oven with the right frequency and the right size, and he built the first microwave oven. So, all because of the Cobra Dane radar array. I mean, that thing is just humongous. That's the concept of it.
Yeah, better ways to spy on it.
Better ways of what?
Spying on
Oh yeah, that is still in use though. That thing still detects a ton of things going on out there, and it's a big deal because now it's a frequency agile array, kind of like the ones they use on the airplanes in the Navy and the Air Force.
Wait, so they can use that one to cook someone too?
Oh yeah. In fact, the airplanes, those 737s or 727s or whatever they used for the AWACS, those are lined with gold foil, the inside of those planes, to protect the operators from being cooked.
Right, but that's like something they can do with that.
Oh yeah, they could easily cook the pilot.
So with the radar array, it's also like self-protective.
Yeah, we could cook Russia, right? We could cook Siberia.
It's not exactly like a death ray.
I know that.
Not really.
But we could microwave Siberia.
All right, so here's a integrated concept, correcting vision with lasers. So this is LASIK surgery, right? It turns out that in LASIK surgery, we're using a 193 nanometer ultraviolet laser, and we're making a spot that's 0.8 millimeters and evaporates a layer of 0.30 micron thick stuff in your eyeball. Right? And so this is how LASIK works. LASIK surgery takes it takes a laser here, and it cuts the cornea of the eye. Well, it doesn't cut it, it shaves it off by evaporating parts of the cornea. And so it reshapes the cornea of the eye so that it focuses the light coming into your eye differently. The problem with this, what's that?
So it's building a lens.
Yeah, well, it's creating a new lens. Your cornea is already a lens.
But like, it's like surgically putting a glasses lens on.
Yeah, what it's doing is it's creating the correct prescription lens out of your cornea. The problem with that is that your cornea is a flexible lens. It's designed to help you to focus. So as you try to focus on something, and your eyes actually, the irises of your eyes actually squeeze the cornea and make it a bigger lens, a thicker lens, or a thinner lens if you relax your eyes. And if you shave off some of the cornea, it weakens that flexible lens. So LASIK surgery actually weakens your cornea. If you take too much off, your cornea can actually collapse the next time you try to focus your eyes. But even if you don't take too much off, over time, your cornea is likely to get weaker and weaker and weaker. So LASIK surgery is not really a great idea if you want to have good eyesight late into life, because your eye will get weaker and weaker and weaker, and eventually you'll need glasses again and maybe even just not be able to see anything. This is something that the surgeons who invented LASIK surgery warned the FDA about, the FDA about this. The Food and Drug Administration, they're the ones that approved this surgery for use in the United States. But they went ahead with it anyway. And why? Because it uses lasers. And the lasers, all the laser stuff is done by computer. So the surgeon actually doesn't have to do anything except set up the patient. They put some rings on the eyeball of the patient to hold the eyeball still. They program in what the patient needs because they know what this patient needs because they've done 1,000 other patients just like this. And so they program in what it needs, and then they let the laser do the work. The laser goes in and bzz, 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 and it's done. Before this, you actually had to cut the eye using a knife by hand. You would cut the cornea in certain places. They call it radial keratotomy because you were making radial cuts from the center of the eye outward. And then as the eye healed, it would heal back into a different shape. And that different shape would refocus the light. But when it healed, your eye would actually heal stronger because of the scar tissue there. And it would leave minuscule scar tissue, so you might have a little bit of refraction in your eye, especially at night, that would cause you some issues with your eyesight. But radial keratotomy would give you perfect vision and stronger vision for the rest of your life. But it requires skill, great skill. So it was very expensive, and very few people could do it. Now, just about anybody can be an eye surgeon. I mean, all you have to do is pass medical school. You don't have to get through surgical school at all. You don't have to learn how to do radial keratotomy. So it all came down to money and people wanting eye surgery. Everybody in Hollywood has to have eye surgery, so they don't wear glasses, so they look pretty or whatever. But not everybody in Hollywood could afford it because most people in Hollywood, most actors in Hollywood are barely making their paycheck. They're barely making their house payment every week or their apartment payments because most actors are pretty poor. Anyway, it came down to politics in the end. It came down to money and politics. Who wants eye surgery? So in this one, they're actually calculating how much energy is needed for that MC delta T because it has to get to 100 degrees Celsius, change in temperature. So you can use that information to calculate how much energy is needed, and then you use a certain amount of energy to evaporate that tissue as well, and so on and so forth. So it's an interesting problem, not one that I'll be doing the homework. Here they talk about how light creates the ozone layer. Light of certain energies, which is related to the frequency, once again. And in this case, the frequency is this little funny shaped V instead of F. But anyway, if you have up in the atmosphere, in the upper atmosphere, you have these this molecule that they call CFCs because it's chlorine fluoride it's carbon fluorochlorines. There we go. So CFCs. But the chlorine is really reactive. So if you add some energy from the light coming from space out there from the sun, it creates this kind of a thing. And when you have the chlorine by itself, it can react with oxygen. And then when you have the oxygen happen, you get these O3 things, and you get this ozone, this breakdown of ozone. So ozone blocks harmful radiation from space. But if you get rid of that ozone because you have these chlorines out there, then you don't have ozone anymore, blocking the harmful radiation from space. And where this is happening the most is near the South Pole and the North Pole. So there's no. It is actually related to also the. It's actually related to the aurora borealis, the magnetic field of the Earth. Where these things build up.
Is that because that's where the strobes kind of expand a little bit?
Yep. So, however, ultraviolet light, which is one of those dangerous radiations from space, is not necessarily always bad. Ultraviolet light can be good. How can ultraviolet light be good? Well, ultraviolet light can do things like it can energize a reaction in our body, in our skin, to create vitamin D, right? So ultraviolet light is a source of energy for some chemical reactions that require that energy. Vitamin D requires that energy to be made. So
Photosynthesis is because of UV light, right?
photosynthesis is actually not because of UV light. Photosynthesis occurs because of more reddish, orangish, yellowish light. Have you seen the greenhouses out here at night?
Oh, yeah.
They're pink. We call them the pink houses instead of the greenhouses. That wavelength of light is actually the wavelength of light that causes photosynthesis. And we get a lot of those wavelengths from the sun, the yellowish, orangish, pinkish colors.
Do they put anything with fish out there?
No. There's a fish hatchery on the other side of the highway. They do some research over the other side of the highway, over by the backflow tower there. But on this side, it's just beef and crops. So what's that?
It's a beef and corn.
Well, yeah. I mean, in that particular greenhouse, the pink house, they'll grow like 10,000 tomato plants in a few weeks and then kill them all. They spray them with herbicides and kill them. It's kind of sad, because I like tomatoes.
So they don't even let them have a tomato.
Sometimes they'll grow some little green tomatoes and might even get a little bit of red tomatoes, but they're growing them so fast that the tomato plant is not very healthy as far as for growing tomatoes. They just need some plant to test the herbicide on. So they'll grow them 24 hours a day. Plants are not meant to grow 24 hours a day.
Yeah.
But if you do grow them 24 hours a day just for a couple of weeks, you can get full-grown tomato plants in 2 or 3 weeks. And so that's what they do. That's why those lights are on all the time. It's to grow them 24 hours a day. Plants usually need about 6 hours of rest every day in darkness so they can recuperate, I guess. So anyway, X-rays are one of these types of electromagnetic radiation. And these X-rays were discovered by Henry Becquerel. Here's a picture of his hand with a bunch of lead shot on it that he took. And it was an accident, actually, that he discovered them. He was doing experiments with uranium ore, and he had a drawer full of uranium ore. And in the next drawer over, and a couple drawers over, actually, he had a drawer full of photographic film that was in its boxes so that it was not exposed yet. You had to take it out, put it in the camera, and then expose it by opening the film. So it was not exposed film, and in between these two things was some junk in a drawer, or whatever it was. And he went to take out this film from this drawer, and he took some pictures with it, and then he had these shadows in his pictures. And he couldn't figure out what they were until he started looking closely, and they were the things in the drawer that was in between the uranium and the film drawer. He had some shadowy images of this stuff that was in that drawer in between, or something like this. And so he started to make this, do these experiments using uranium fragments, and discovered that there is a type of ray, and he didn't know what it was. He called it an X-ray because it was this mysterious ray that could travel through wood of the drawer and make an image traveling through the objects in that drawer, and travel through the boxes on the film, which were usually made of wood or something similar to that, so it could travel through things. This mysterious X-ray, right? And then he started to make experiments with his hands and with other things. He made his first medical X-ray was done with somebody that had a broken hand or a broken arm or something, and he was able to see the broken bone. And he also discovered that this could be used to treat things. Well, he didn't, but other people did. It could be used because it was damaging to skin. It could be used to treat cancer. They figured that out almost immediately, that they could actually kill off the cancer with the X-rays. And it did a little damage to the other tissue around it, but it killed the cancer at least. And so that was the first radiation therapy.
Did he die early?
He did not die of radiation poisoning, although the Curies, who are the pictured up above and down below here also, they did. They were, they did a lot more experiments with a lot higher radioactive stuff, like radium and radon and stuff. And so they did die of radiation poisoning. But another thing that eventually they discovered that X-rays are just a kind of light, and that that light had a very, very short wavelength, and it could you could actually use it to make a picture of something that needed a very low resolution because it had a very short wavelength. Remember we said smaller wavelengths give you higher resolution. So blue light gives you higher resolution than red light. Well, X-rays are even smaller than blue light. And it was this woman over here, what's her name? This woman on this board here, Rosalind Sussman-Yalow. She did experiments trying to take a picture of biological molecules. Particularly, she was looking at crystallized molecules inside of at the center of the cells of plants and animals, plants in particular. And they were trying to figure out what were these molecules that kind of looked like little strings at the center of cells. Well, what are they? They're DNA. And they suspected that they kind of knew that they had something to do with replication, making one cell to another cell, because they could see that happening. But they didn't know, what they didn't know is what it looked like at the molecular level. And they were able to use X-rays to go through these crystals of DNA, and they were able to show that they were helical in shape. So she was the one that discovered the helix of DNA. Now, it's often said that Crick and Watson discovered that because they were given the Nobel Prize for it. But she was the head researcher. She died before the Nobel Prize was given. She may have died from poisoning as well, but I don't know. But she did die before the Nobel Prize was given, so they couldn't give it to her. It's the rules of the Nobel Prize, you cannot give it posthumously. And so she missed out on that, and as a result, her work is mostly attributed to the two people that worked with her.
2 lab assistants.
What's that?
Or 2 lab assistants.
They weren't necessarily lab assistants, but she was the one that did kind of the seminal work. She was the one that was really pushing this forward. And they took that work and finished it, I guess, is a good way of saying it.
So she should have had a Nobel Prize, right?
Yeah, and if they'd given it to her before, if they'd awarded it before she died, she would have. Many people have died before they could receive a Nobel Prize who deserved it, unfortunately. But that's the rule. Nobel, who's the inventor of dynamite, he's the guy that invented dynamite, he created the Nobel Prize and made the rules, and they can't be changed. So there's all kinds of weird rules about the Nobel Prize. The Nobel Peace Prize, for example, whoever wins the Nobel Peace Prize sits at the right hand of the king at the Nobel Peace Prize dinner. Whoever wins the Nobel Prize in physics sits at the left hand of the queen. So, and then every one of the prizes sits at a particular table. The further you are from the king and queen, the less important he thought that prize was. So chemistry was next after physics. And then I think maybe literature was next or something like that. But he had what he thought was most important. The Peace Prize was first, physics was second, I think chemistry was third, which was interesting since he got his money through chemistry. But he was really fascinated with physics as well. But peace was his biggest thing. He really hated the fact that people used dynamite in war. He hated that got used for war. And so he made the Peace Prize the most important one. And gets the most money, too. Anyway. So, gamma rays also were given the name gamma just because they decided to, I don't know. They just said everything that's, shorter frequency than what we're going to call X-rays, we're going to call gamma rays. So it makes the Hulk, But gamma rays will go through just about anything. Gamma rays can be so energetic that they can just take apart matter. So when you have a nuclear bomb explode, the first thing that comes out of a nuclear bomb is gamma rays. And those gamma rays are so energetic that depending on the size of the bomb, but for meters and meters in every direction, everything just becomes completely disintegrated. It just gets taken apart down to like atomic level and below. Bigger atoms get broken down, molecules get completely disintegrated, and and even some bigger atoms actually get taken apart. And so but it is mostly molecules that get taken apart. So you have just nothing but atomic dust, right at the epicenter of the bomb, and that's done by pure gamma. That's done before there's any light coming out, visible light. That's done before that happens before any blast comes out. That's before any heat comes out. This gamma ray burst comes out and just disintegrates everything for meters in every direction,
including most of the bomb.
including most of the bomb.
So you'll never find nuclear bomb fragments.
Well, no, that's not true. They're just usually very small because it won't break down the uranium or the plutonium from the bomb. It definitely won't do that. So the uranium and the plutonium from the bomb is still intact.
They use it to identify where the material is.
That they can actually find it because it's highly radioactive. It's very easy to find radioactive things, but when they end up finding it, it's usually attached to other things as this atomic dust blasted outward after the blast. It attaches itself to things that aren't taken apart. And so they, a piece of wall, a piece of something, might even be a piece of, I don't know, whatever. It's just some piece of something that it's attached itself to. And so they have to correct all these pieces of things that the bomb material has attached itself to. And they can usually, they were able to retrieve like 99% of the stuff from both the bombs they dropped in Japan and all the bombs that they drop out in testing grounds. They're able to get pretty much 100% of it. 99.99. Some of it goes in the atmosphere if it's an atmospheric explosion, but they haven't done those in a long time. So anyway, it's not that hard to track it down. Is that really only our first section? You gotta be kidding me. Oh no, this is our fourth section. We're done. This is the last section, right? Okay, so energy. How do we calculate the energy? Well, it has to do with the intensity of the wave, and the intensity of the wave is done through some calculus. There's an intensity of the electric wave and an intensity of the magnetic wave. And to get the overall intensity of both, it's actually a fairly easy equation, simple equation. You take the electric field times the magnetic field and divide by 2 times the permeability free space. That was the 4 pi times 10 to the minus 7 number that we had in electromagnetism, or in magnetism. So that's how you calculate the intensity. Intensity, remember, is watts per meter squared. That's how much energy per time you have over an area, a surface area. So in this particular example, we have a microwave that's projecting 1 kilowatt of microwaves onto a 30 by 40 centimeter area, and we want to know what is the intensity. The intensity is going to be this power divided by this area. Power divided by area, pretty simple. But if you wanted to know the electric field for that, then this intensity would be used in the intensity average equation, which is this equation here for the electric field. That was one of those previous equations, solved for electric field. And then you would solve that by plugging in that intensity average that you just calculated. Oh, and then also the peak intensity. So this one uses the average intensity, but if you want to know the peak intensity is generally about twice the average intensity. So that gives you I0, which is peak intensity. And then magnetic field strength, the easiest way to do that is to just use the electric field that you already have. You've already calculated the electric field from the peak intensity, or from the average intensity here. So you just use that one, divide it by C to get the magnetic field, and you're good to go. So it's pretty simple, just plugging things into simple equations, nothing very difficult in that chapter. And we're done. So that's chapter 24.
All right, so how do you figure out which light color is brighter is like some of the questions?
Like which one's in which part of the spectrum? You look at the spectrum. Look at that chart and say, I've got this wavelength. Where does it line up? Right about there. I've got this frequency. Where does it line up? Right about there. Remember that higher frequency is higher energy. Right? Higher frequency is also lower, smaller wavelength. Bigger frequency, smaller wavelength. Bigger frequency, bigger energy. And vice versa.
So where are you going? Alright.
All right. You guys working on homework today, or?
I'm gonna go get my textbook.
I have to study for counting.
Okay. Well, then we'll call it good. Enjoy the homework.